Hello and welcome to CMG's webinar on optimized polymer injection through modeling from lab to field. My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'll be today's moderator for this session. I'm pleased to introduce Fraser Scorreco, Chief Reservoir Engineer at CMG, who will be presenting today's webinar. Fraser has over 35 years of industry experience and has been with CMG since 1993. Throughout his 23-year career at CMG, Fraser has remained focused on providing technical expertise and guidance to the oil and gas industry on simulation and application of advanced EOR processes in the field. He specializes in various chemical EOR processes, including ASP, foam, as well as in-situ combustion and other recovery processes. Fraser holds a Bachelor of Science degree from University of Calgary. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your questions at any time using the chat window on your screen. We will also post the recorded version of this presentation on our website within the next 24 hours. You can use your CMGL username and a password to access the material. Over to you, Fraser.
All right, thank you, Anjani, and good morning or good evening to everyone, depending on your location. As Anjani said, I'll be talking about optimized polymer injection through modeling from lab to field. The agenda for today will be, first of all, introduction. We'll talk about some physical phenomena involved, some laboratory matching, how we typically do it, then some scale up from laboratory to field scale, and then a small polymer injection optimization study. If you notice, the picture on the right here is how polymer normally is delivered to the field. It comes in bags. It's a dry powder. It does not come as a solution or a liquid. So introduction, of course, polymer, it's a EOR technique in which polymer is first mixed with water, then injected to the reservoir to increase the water viscosity. It's that water viscosity that provides the mobility control and yields a better sweep efficiency. So a summary of the physical phenomena involved. First of all, for the water phase, it's the higher water viscosity that we're after. There's a polymer viscosity versus shear rate effect. And then there's also a viscosity versus salinity effect. For the oil, there's really no reported effects. For the rock, there's absorption, there's inaccessible pore volume, there's SOR reduction, and residual resistance factor. And then there's also polymer degradation. So first of all, the water viscosity. The plot on the left is showing what the viscosity may look like as a function of polymer concentration. So as you add more and more polymer, you get a higher water viscosity. And of course, that gives us an improved mobility ratio. The formula for mobility ratio is just here, the K over mu, water over oil. And then the plots on the right side show what your sweep efficiency may look like, you know, and maybe with a medium heavy oil where you get a lot of water viscous fingering. And then on the bottom is what it might look like after you add polymer. Your flood front is much more uniform and much more improved. Now, viscosity versus shear rate effects. The polymer is a non-Newtonian fluid, so you do have a viscosity change with velocity or shear rate. Plot on the left is showing a typical shear thinning behavior, a plot from Builder showing the shear rate log on the x-axis and viscosity on the y-axis, showing how the viscosity will decrease with increasing shear. The plot on the right is showing a plot where you have shear thinning and thickening together. You can see here again, the x-axis is the log of the shear rate. You first of all get shear thinning, and then at some point you begin to get shear thickening. So you can model both those effects, but most commonly we model shear thinning. Now another phenomenon involved is the salinity effects. Now this plot is showing a typical behavior of polymer viscosity versus salinity. As the salt concentration increases or salinity increases, the viscosity will decrease. The reason for that is that the higher salinity causes a structural change in the polymer, decreasing the ability of the polymer to cross-link. Now, in CMG software, you can define salinity to be any or all of the ions that are in the model. Typical ions that we use for salinity are sodium, sometimes calcium, magnesium, chlorine. You can choose any or all of those. And the way we model it in CMG software is to use this analytical equation here, where the polymer viscosity is a reference polymer viscosity times the salt concentration in any particular grid block divided by a minimum salt concentration that is user input to the power of this SP number, which is also user input. So there's two values that the user must input for this correlation. And then what the simulator will do is it will calculate this XNaCl will be the salt concentration at any particular grid block. So each grid block is going to have a different salt concentration. It'll have a different polymer concentration based on this salinity. Now, there's also the injected salinity as well. So what happens is the injected salinity that's that the polymer is mixed with will then mix with the in situ formation water salinity, and you'll get some different salinity in the reservoir. And of course, it depends on your reservoir, your initial salinities. You might even have a salinity gradient in your reservoir. So you could have quite a complicated behavior with salinity, and it's, like I said, it's going to change with every grid block. Now, another phenomena is the requirement to use multiple polymers, and this is usually when it's when polymer is injected with alkali, as in an ASP flood. So one of the first reasons is that polymer will have different viscosity depending on the pH of the system. So as you inject alkali, the pH will go up. So an increase of pH will cause an increase of the polymer viscosity. So that's one reason why you want to use multiple polymers. Another reason could be if you have a significant amount of calcium in your reservoir, that will cause your polymer to precipitate. It's, conventional HPAM polymers, especially if the reservoir temperature is high, like above 70 degrees C. So during alkali injection, there's little chance of exposure of polymer to calcium. But after the alkali, during the flush of the ASP, one would have to do one of the following: either continue softening, in other words, removing the calcium, or continue alkali injection at a lower concentration, or switch to a calcium tolerant polymer that's usually more expensive. So whatever approach you choose, of course, will depend on which is most cost effective. Now, another phenomena to do with the rock is the absorption. So this little movie is showing what might happen in the reservoir, where some of the polymer is absorbed onto the rock until it reaches a maximum sort of saturation limit beyond which no more absorption will occur. And then when polymer injection is stopped, then you'll come down to a residual absorption level, which may or may not be close to the initial absorption value. So this residual absorption could give you additional mobility control effects. Now, another phenomena tied to the absorption is the residual resistance factor, or RRF. Now, this plot here is showing a typical core flood. You have pressure on the y-axis and then pore volume on the x-axis. The first curve here is the initial water flood, and at the end of the water flood, the pressure here is 20 kPa. That's also delta pressure, 20 minus this 0 value here. And then you inject polymer, pressure goes up quite a bit, and then the water flood after polymer, it drops down to 60 kPa, and it doesn't reach the initial values that was during the water flood. So this change here from 60 kPa over 20 kPa is really your RRF, so 60 over 20, and in this case it would be 3. So core floods are usually the way that that we get our RRF values. It's not that easy to always measure it directly by other means. Now, additional phenomena that could be important is the RFT is a function of permeability, and the reason for that is that the polymer molecule is typically quite large, so the amount of plugging will depend on the pore throat radius, because these large molecules cannot flow through the smaller pore throats, and pore throat radius is proportional to permeability. A second phenomena is that RFT can be phase dependent, so that oil and water flows differently, and that will control your breakthrough times, and you can use that for matching your field cases. Now, another phenomena is the inaccessible pore volume, and it refers to the connected pore volume at which these large polymer molecules can contact and occupy. And this picture here is showing how the polymer may flow through the larger pores, but then become trapped on these smaller pores. It just cannot flow through it. So this inaccessible pore volume is linked to porosity, permeability, polymer molecular weight, and porosity distribution and size. The inaccessible pore volume can be used as a history matching parameter to match breakthrough times in your field studies. Typically, we do not get this from core matching or core floods. Now, another phenomena involved is the residual oil saturation reduction. This plot is showing your typical desaturation curve, where the log of the capillary number is on the x-axis and the residual oil saturation, the SOR, is on the y-axis. Now, the capillary number is given by this equation here, viscosity times velocity over interfacial tension. So as you increase the water viscosity with polymer, you move down this curve somewhat. So your reservoir flow may be somewhere around here, and then as you increase the viscosity, you'll move down this curve somewhat. Obviously you're not going to move down as far as you might with alkali injection or ASP, where the interfacial tension becomes very, very low. I mean, with ASP, you'll move way down here, very close to a zero or close to zero residual oil saturation. For polymer, you'll be up further on the curve here, so there'll be some small deviation or decrease, but as I said, not as much as with ASP. Now, another phenomenon involved is the viscoelastic effect. So not all polymers will exhibit this. The viscoelastic type polymers will increase the thickening, and when that occurs, it'll alter the pressure field, which will destabilize the trapped oil. So you will get a reduction of SOR with viscoelastic polymers. And it'll depend on the molecular weight of the polymer, the permeability and porosity, but not the concentration of polymer. And that viscoelastic effect can reduce the SOR even more than just the effect of capillary number that we talked about on the previous slide. And this plot is showing a plot from the Chinese Daking field with HPAM polymer. It's permeability on the x-axis, the molecular weight on the y-axis, contours are the flow velocity. So just showing that at the higher molecular weight, higher permeability, you'll get more of this viscoelastic effect. Now this plot is showing a typical core flood in which we inject polymer, and the increase in viscosity shows up as a substantial increase in the capillary number. So our viscosity is increased from slightly less than 1 to almost 11 centipoise. And that change has caused the capillary number, in this case log of the capillary number, to increase from -6 to about -4.5. So that change is going to give you some SOR reduction. Now another phenomena is the polymer degradation. This one is typically ignored in many simulations, but there's various types of degradation. The chemical degradation of polymer, this is mainly controlled by oxidation reduction reactions due to the presence of divalent cations such as calcium, magnesium, or iron. There's also thermal degradation. Typically below 50 centigrade, the polymer should be stable for long periods of time. Between 60 and 70 centigrade, the stability will depend on divalent ion concentration and the molecular weight of the polymer. Above 70 degrees C, you could get significant degradation or precipitation. And with higher molecular weight polymers, the degradation is greater. There's also biological degradation, and that's caused by bacteria in the reservoir. There's also mechanical degradation that occurs when the polymer is exposed to very high shear conditions, causing breakdown of the polymer. Now this plot here is a typical plot from the lab where we see significant amount of polymer degradation. The viscosity decreases almost by a factor of 3 in only 60 days for these 3 different polymers. So in this case, there was fairly significant degradation. And we model this in CMG software using a first order reaction of polymer changing to water. Now another issue with polymer is injectivity loss, and it'll depend on the increase of water viscosity due to the polymer, the polymer absorption, and the residual resistance factor. And the match of the lab core flood pressure is critical for predicting this injectivity loss, This plot on the right here is just showing the top plot is oil recovery. It's matched fairly well. This simulator is the red and the lab data is the blue points. The pressure is down below. It's matched well up until the end of the first slug polymer injection. And then the simulator drops below the measured value. So there's some residual value here that's not captured properly. And same thing, if not worse, on the second slug, there's this substantial difference here. So that would mean that the injectivity after polymer injection stops would be too optimistic as predicted by this particular model. Now, the injectivity loss can be mitigated by shear thinning effects at high velocities near the injection well, the creation of microfractures near the injectors due to high injection pressures. That's been reported by many operators, and also dilation effects in unconsolidated sand. So typically what happens in many field cases, pilots or whatever, is that the field injectivity is higher than what was predicted by the model. So these last two effects can explain that. Now the question becomes, what simulator should I use? As all three simulators have polymer modeling capabilities. As you can see, STARS and GEM both have very similar features for modeling polymer. So if you need some of the more advanced features of polymers, for example, like salinity or degradation, then the choice between STARS and GEM will really come down to your fluid type and what you want to compare it to. Like, for example, if you want to compare polymer to steam injection or hot water injection, then STARS would be the obvious choice. Or maybe your fluid, your oil is a very light oil. You might want to compare polymer to miscible flooding. And in that case, GEM would be the choice there. And then, you know, if you don't need any of these more advanced features, then you can use IMEX to get you kind of more of a screening type predictions. So the typical workflow, first of all, we start with our lab core flooding, the history match, and we'll typically use our package called CMOST for that. And then we'll do upscaling, and then move to usually some kind of a pilot field case. This particular one is just a inverted 5-spot pattern where you do predictions on a pilot model. And then you would typically take that and do a optimization study and optimize your polymer to come up with something to use for your full field case. Now I'll do a quick demo on how to model polymer using Builder. And we're going to use our the process wizard, just the panel showing here. So I'll switch to launcher now, and like I said before, both GEM and STARS have very similar features. So when you use the wizard, it'll look very similar. So I'll just use a STARS based data set and start Builder. And I'll start the process wizard here and select the option for alkali surfactant foam or polymer. Click next, and I'll select polymer flood here. So now we have a number of input options here that we can choose. First one is viscosity as a function of salinity. Normally you should use that because that is an important effect. So we'll check that one. Now you notice once we check that, now it's asking for an initial salinity for all blocks. So we'll enter a value of 50,000. Now, if you have a salinity gradient in your reservoir or different zones of salinity, you can modify this after using the wizard. And I mean, it's a grid block based property, so you can change it for every grid block if you want. Now, another feature that we can model here is the SOR reduction. So we can check that, and once you do, it's asking for a bunch more input here in this purplish color here. The first one is the SOR reduction. That's really the SOR from EOR divided by the SOR from water injection, our normal reservoir flow. Now, the value of 0.5 might be a little bit low for polymer. We might want to use a value of say 0.7 or 0.8. So let's just try a value of 0.7 here. The KRW change, normally you should not have a wettability change with polymer. So we won't change the KRW, we'll just leave it at 1. So again, that's just a factor, this ratio of KRW EOR divided by KRW for water injection. Also, the capillary pressure should not change. We're not trying to model any wettability change here, so we'll leave them at 1. Now you notice down here that there's also some special options for special well perm handling. This is typically used for one case when it's an oil wet carbonate. The SORW may be quite low because the SORW may have come from centrifuge data, giving you a very high capillary number, very low SOR. Another case might be if your rel perm curves are normalized. This could be either clastics or carbonates. If you do have oil wet carbonate and this kind of a situation, probably it's best to use this first option here, to use this delta KRO, and there's a couple of inputs there. I'll just show you what the results could be from using that option. It would be something like this, where you have a KRO change here. So your normal reservoir flow case was this blue curve here. It's not 0 here, but it's a very low value. So your SOR is actually quite small. This blue curve doesn't become 0 until it's about 0.95 water saturation, something like that. And then the modification is to increase the KRO, and you have a fairly flat curve here, and that corresponds to the typical oil wet behavior of carbonates, where you need many pore volumes of water to recover that oil. The oil clinging to the rock surface, it's difficult to get out, but once you do flush it with many pore volumes, you do reach a very low SOR. So this curve is representing that oil wet behavior. So we'll just go back to Builder here. But I mean, for this example, it's not an oil wet carbonate, so I mean, we can leave that option checked, but it's not really going to do anything. Now, another input option here is the polymer degradation. This polymer quantity decreases with time. When you choose that option, it asks for a polymer half-life in terms of days. This one is about 3 years, so a fairly slow degradation, but still there is a degradation. Now what that will do is the wizard will set up a reaction, a first order reaction of polymer just changing to water. So we'll click next here. This is just showing the components that will be added. There's only one rock region here, so we'll just select that. This is the input for the polymer absorption. The default here is at 0.1 weight percent polymer. The absorption is 50 milligrams per 100 grams of rock. we'll just use the default here. Now here is the panel where we input our lab polymer measurements. Now we see here that we have weight percent polymer and viscosity. We wanted the salinity effects included, so I'll just input one more salinity here, say 10,000 ppms. Once I do that, then we have the wizard has supplied us default values at different salinities, and we also want to model the shear rate effects here, so we'll choose that. And so now we see some default values from the wizard. Now this is where you would input your lab data here instead of what is supplied by the default wizard values here. Now once you've input your lab data, then the idea will be to match that lab data with what the simulator is going to predict. So we can change the plot here to be, first of all, polymer concentration and velocity. So now we can see a plot here of different velocities. We can also change it to be to put velocity here or shear on the x-axis. Now I'll just put up the legend there for a moment so we can see what's going on. So now we can see that these curves represent different weight percent of polymer. Now in this particular case, our injected polymer concentration is 750 ppms or 0.075 weight percent. So we need to change that here. So that'll be our polymer injection weight percent. And we need to make sure that that particular one is matched the best, because that is going to be the one that is most common throughout the reservoir at this weight percent. So you can see here the default is that that's matched fairly well. The other ones are not matched as well. We can try to improve that match by changing the curves used to calculate the nonlinear viscosity. That one didn't really change it very much. We can try a different one here. You can see here now that our magenta curve is not matched anymore. The blue one is a little bit better, but that's clearly not as good. So in this case, most likely the first one was the best match, because the most critical one is to match our injected concentration. So once you're happy with this match, you can also change this plot to look at polymer concentration versus salinity. And here again we see that that our injection concentration points are matched very well. These 2 points here. This curve here at the lower salinity is matched quite well. At the higher salinity, these 2 points are not matched as well. But the most important is our injection composition here. So once you're happy with this, then click Next. You can input your injection compositions here, 0.075 weight percent polymer at say 10,000 ppm salt, and choose our injection well and the injection time, and click Finish. We can look at what we got from that by looking at the rock fluid diagnostic plots here. And here we see that the wizard has added our set number 2 curve here, this magenta and green curve, where we see a shift in the SOR. The only reason we see an apparent shift of the KRW is just because of this shift in the SOR. We actually have not changed our KRW curve. So now I'll just go back to our presentation and continue here. So now we'll go through a laboratory history match. And in this study, there's actually 3 different polymers done. We'll just look at the polymer number 1. So for this task, we use CMOST, and CMOST is CMG's tool for various tasks here, like sensitivity analysis, history matching, optimization, or uncertainty analysis. Now for this core flood match, we use CMOST for the assisted history match, and it uses advanced algorithms and creates combinations of the most influential parameters to achieve a history match. So of course, we're looking for the lowest possible error here. This red point here is our best history match here at quite a low global error here compared to where we started out at very high errors here. So in this particular case, the parameters used that were sensitive are the maximum polymer absorption, the residual polymer absorption, the resistance factor, the accessible pore volume, and the SOR reduction. Now the parameters to match, or the objective function, was the cumulative oil production measured in the lab, the injector BHP, and the produced polymer concentration. Now the match results are showing here, showing that we got quite a good history match of this core. Cumulative oil pressure and polymer production are all matched quite well. And as you can see by this plot of error reduction, our global error was quite small after 350 some runs, and the actual values that it came up with are showing here on the right side here, the absorption, residual absorption, inaccessible pore volume, and RRF. And you notice that the RRF is this 2.9 value. Typical values for the RRF should be between 1.5 to a maximum of 4 or 5. Anything higher than that is probably not realistic, and there's something else going on in your core flood or in your model. Now we'll look at scaling laboratory to field scale. And what we typically do is take our lab core flood, we scale it up using the same parameters and the same core, or the same block dimensions, except they're just scaled up to field scale block sizes. So we sort of call that our mega core model. And then we can take that directly to our field model, since the grid block sizes should be the same. Now this slide is showing some scale-up parameters, some scale-up theories from the literature, these different SP papers, and they're all using these different ratios of the model to the field scale, this RL value. And you can see here from these different methods, they're all slightly different, but similar, but none of them preserve velocity. All of them are using 1 over this RL value. The problem is that polymer is velocity or shear dependent. So we need to make some small modifications to these to be able to preserve velocity. So you can see in this slide now that we have 2 different methods to preserve velocity. As I mentioned, we need to preserve that velocity for polymer, but then we have a bit of a dilemma. with our models, because if we preserve velocity one way, we can preserve pressure, but then that is not going to preserve shear. The problem is that in our models, depending on what our model is, we may have pressure dependence of some properties, and it's typically viscosity. If you're using stars, you may have multiple viscosity tables at different pressures, so you could have pressure dependence built in there. If you're using gem, then there will be a pressure dependence of your viscosity there. So like I said, it's a bit of a dilemma. So if we preserve pressure, then that means that shear is not preserved. So this is the equation for the shear. You see it's velocity is proportional to velocity, and permeability is down here. So this method here to preserve pressure does not preserve shear, because permeability is scaled by this RL number. So then we have another method here where these two are reversed essentially. This one will preserve permeability, so that in this case shear is preserved, but then pressure is not preserved. So depending on your model, you may need to use one or the other of these methods. You may need to use both depending on your model. For example, if you have stars with no pressure dependence in your viscosity, then it's okay to use this one to preserve shear, because you do not have a pressure dependency. Now, upscaling of the laboratory data, it's useful to verify that the field scale model will duplicate lab scale results. Usually you'll be able to do that no problem. We've done many of these, and usually you'll be able to scale it up no problem. You need to verify whether your reaction rates need to be upscaled, and the reaction rate that you might be using for polymer is the polymer degradation. And you could use it to result in the field scale capillary numbers to use for Rel-Perm interpolation. That again is the case if you're using SOR reduction. And due to field scale model runtimes, many times the grid block size is larger than required for polymer. Previous experience has shown that if your aerial grid size is 10 meters by 10 meters, then there should be no problem with any grid size sensitivity. If anything larger than that is used, then you need to do grid size sensitivities. Now I'll go through a quick study of polymer optimization. Now again, CMOS was used for this, except it was used in the optimization mode. So for this study, there was 3 different polymers used. Each of them had different viscosities, different absorptions, different residual resistance factors, and different accessible pore volumes, and different costs. Polymer 2 was the most expensive. Polymer 3 was the least expensive. So the parameters used for optimization were the injection fluid, the 3 different polymers. Also, we included water there to make sure that that we were making money as compared to just straight water injection. Polymer concentration was varied. Those 5 different concentrations were used. The water and polymer slug sizes were changed, and the injection rate was changed. Now the objective function was the net present value. CMOS has a built-in calculation of net present value. It's a fairly fairly basic calculation, but can be quite useful. For this calculation, we used an oil price of 55 US per barrel, maybe a little bit high for today's prices, but that's when the study was done. There's a water treatment cost used, and then of course our different polymer costs, and everything was discounted at a yearly rate of 10%. Now the results are shown in this plot here, where our initial base case started way down here, and our optimized case was up here. This red point here is our best optimized case. And in this study, we did about 450 runs, but you can see here that even after slightly less than 50, CMOST came up with a fairly good optimum. So I mean, if your run times are longer, you don't necessarily need to do 450 runs. You might do much less and still come up with a good optimum. Now the results are shown here in these three plots of water injection rate, cumulative production, and injection BHP. You can see here that our optimized case is this red case here. Our base case was the black case, the black line here, and then all of our different runs here are shown in the blue cases. But you can see that our injectivity was decreased by the polymer, and in this study we actually did assume that there's microfractures created. The problem is that the injectivity was limited due to maximum frac pressure. You can see that in this last plot here, that our injection pressure was limited to 2,000 psi because of our limiting frac pressure. Now you see here that our cumulative oil production, our optimum case was not necessarily the maximum cumulative oil. It was close to it, but not. It was not quite at the maximum. So if we look at some cross plots done in CMOST, you can see the results of the run much more clearly. And what it showed us is that our optimum case was the lowest polymer concentration at the highest injection rate. And that's because, again, of our maximum limiting pressure limited by fracture pressure. And as I mentioned, we did assume that there was microfractures created near the injection well in this study. So the best strategy is listed here. It was polymer 3, which, if you remember, it was the cheapest polymer, the lowest concentration at the highest injection rate, and at the polymer pore volume injected at 0.7, the slug duration of a little over 2 years, and that resulted in an incremental oil of 260,000 barrels and an incremental net present value of $7 million US. So in conclusion, we see that IMEXGEM and STARS are capable of modeling polymer injection. CMOST is a very useful tool for both history matching and optimization. In this case, it was used for both, and it gave us a good optimum technical and economical strategy to use. The result of that was that polymer 3 was selected as the appropriate fluid to be injected, as it gave additional oil and a good increase in the net present value. And with CMOST, we obtained a strategy that has 262,000 barrels of additional oil with $7 million US of additional income. Thank you, everyone, and now we'll deal with the questions.
Thank you, Fraser. We will now take up questions. If you have any questions and haven't submitted it, you can do it online using the chat window on your screen. I see there are several questions already submitted, so we'll try our best to take as many questions as we can. And we'll start with the first question here. The first question is from Jack. And the question is, can stars model the viscosity reduction as a function of surfactant concentration?
The viscosity reduction so with surfactant and polymer, yes, you can do that in your table of viscosity versus temperature. There is a column for surfactant. So you should be able to input a value there and model viscosity change effects there.
Okay, so the next question is from Mohsin Rafi, and the question is, how did you define your pore volume value and design your slug size in the optimization study that you presented?
The pore volume was actually an optimized parameter from CMOS. So we input a range of pore volumes in CMOS, and then it was handled by a trigger in stars. So we made the trigger a CMOS variable, and so the trigger at which the polymer injection stopped would determine basically the pore volume injected.
The next question is, what is the Corey exponent that you used in the study? How did you get this number? Is it possible to determine it from the lab?
The Corey exponent was determined by matching the water flood portion of the core flood. That was not really covered in this webinar. That was done in the actual study, but that's normally how you would come up with that. You would match the water flood portion of the core.
The next question is from Bilal Aslam, and the question is, how do microfracture near injection well is modeled? Is it pressure dependent?
You can model it with pressure dependency in stars. There's a keyword called P-trans that will do that. It depends how prevalent you believe your microfractures are. If you believe they're very close to the injection well, you can model it with an increase in your well index if your grid blocks are fairly large. If your grid blocks are very small, you might want to use that P-trans keyword.
The next question is from Sandro, and the question is, the example you show at the very end, how different will you expect the result if you use a more realistic degradation of 2 months half-life for the polymer?
Okay, if you use that kind of degradation, I would call that a severe degradation. I mean, that was actual real lab data, but just because it's real lab data doesn't mean you would actually use that in your real reservoir. If you use that kind of a severe degradation, you would get a lot less incremental oil.
The next question is from Imad, and the question is, in the optimization study that you presented, a 0 pore volume water injection was recommended. Does this mean polymer slug is applied in the secondary mode?
That is correct, yes. That CMOS was showing that it's better to do polymer injection right from the beginning.
The next question is from Kafiz Muradov, and the question is, can you model mechanical degradation across restrictions in the wellbore?
Yes, you can model mechanical degradation. I'm not sure what you mean across restrictions in the wellbore, but
I think it means across perforations.
Yeah, I mean,
or across completions.
Yeah, I mean, you could model it in stars. There is a velocity dependent property for reactions called MT-vel, I believe it is.
Yeah.
So you could use that to make your reaction velocity dependent.
The next question is from Samson, and the question is, in stars, can you model adsorption as a function of concentration of another component?
Yes, in both stars and GEM, you can do that. You can make it a function of two different components. There's a keyword, a sub keyword of from absorption of 2-CMPW.
The next question is from Saujatya Mukherjee, and the question is there any special model for modeling biodegradation of polymer in CMG other than using the first order reaction kinetics?
No, there's nothing special for biodegradation. Biodegradation, you would have to add components for the something in the reservoir that is causing this biodegradation, and set up a reaction with that component. You would of course need some kind of laboratory data to tune that reaction.
The next question is from Mohammed, and the question is, we could not model viscous fingering in our lab and field modeling. Does CMG model viscous fingering?
Yes, but you need a, well, viscous fingering is normally modeled through your rel-perm curves. So you would have to use rel-perm curves that kind of show that sort of behavior, a fairly quick water breakthrough with low oil recovery.
As well as you may have to end up using finer grids to replicate that behavior as well.
Yeah, definitely finer grids.
Yeah. The next question is from Imad, and the question is, you talked about both maximum and residual adsorption limits of polymer. Can you elaborate more on residual polymer adsorption? What you mean by that? Is there any other way of getting this value other than history matching?
There's not really any good method of measuring that in the lab other than doing a material balance in the lab. Basically, production divided by injection. If you don't produce back everything that you've injected, then whatever is left in the core after flushing it with water should be your residual value.
The next question is from Mohammed Sadeh, and the question is, can CMG model associative polymers?
Associative? Not exactly sure what he means by associative polymers.
I think what he means is probably like a secondary polymer as a second component, which we can in stars.
Yeah, I mean, if it's two different polymers, we can do that. Or, I mean, if there's or maybe it's a cross-link, a cross-linker, and if you want to do that, yeah, you can model that in stars. You just need to use two components and a reaction.
Okay, the next question is from Mohammed Yusuf, and the question is how to model for heterogeneous carbonates at mature water flood stage for a low matrix permeability reservoir with thief zones at the top and the bottom of the reservoir.
Well, I'm not sure you would do anything specific for that. I mean, that sounds like a perfect case for polymer. You you would probably want to use a more viscous polymer to try to reduce the mobility. You might even want to look at gels in that case if you really have such thief zones like that.
I think we have time just for one more question, and the question is from Khalid, and the question is, can we model shear impact on viscosity at well completion level, example across ICDs or FCDs?
Yes, we can in stars if you use our flex well feature to actually model the flow inside the well.
All right, there are several other questions, but I think to honor the time with our attendees, I think we'll stop the question and answer session at this time. But however, we'll get back to every one of you with responses to your questions. And I hope you found today's webinar useful and it helped you in getting a better understanding of some of the mechanisms involved in the polymer injection processes, as well as some of the features and capabilities available in CMG simulators. CMG does offer a multitude of training courses for all skill levels, and for those who are interested in knowing more about this subject on chemical UR as well as polymer injection, we do offer several chemical UR courses as part of our standard training course, which you can find on our website, as well as we offer company-specific customized courses suitable to your needs. So for more information on our training course offerings, I invite you to look at our website. We will post today's recorded presentation within the next 24 hours. You can use your CMGL username and a password to access the material on our website. If you have any other questions related to the material presented today, or would like to know more about our product offerings, please do not hesitate to contact us at sales@cmgl.ca. So again, thank you for attending today's webinar on optimized polymer injection through modeling from lab to field, and hope to see you guys next time in our next webinar. Thank you.